Now that we are able to approach a function how closer we want with respect to a point, we can start to measure how things change in that function and around that point. So we want, and remember, our goal in this course is to measure the instantaneous change of a function on a certain point. So let's define the difference quotient. Here we start from the simplest possible function, a univariate function that goes from a real number to another real number. And we start by looking at a point x0, which has its image as equal to y0. We say that delta y over delta x is the difference quotient and is equal to f of x0 plus delta x minus fx0 over delta x. We can see this through this graph. So this delta refers to delta y divided by delta x. And this is the slope of this line. If you remember how the line can be the parameters of a line, the intersection and the slope can be found given the two points in which that line passes through. So we have that we are just defining the slope of the second line to the 2 points on the graph of S. The 2 points are x0 and x0 plus delta x. Here, and we have the images as the y coordinates. Now we can take the limit of delta and define the derivative if exists. Can be expressed in this way, or even with a prime on f. We will see in the further slides several ways to describe, to write a derivative. But this is just notation. Let's see how we can compute it. So we are computing the derivative of x with respect to x0. We take again the difference quotient, but now this delta x becomes h, and we are taking the limit of h that approaches 0. What we are doing here is take f of x0 and a point near, very close to x0, taking its image and see how the changes is performed by f with respect to the change we have done in the domain. In fact, this h is the result of x0 plus x minus x0. So again, we are dividing the delta of the y's with respect to the deltas of the x's. But here we are taking the limit. We are going closer and closer to x0 and its image fx0. The derivative exists only if the limit exists. Let's take a look at an example of derivative. with respect to a generic point x. The function can be written as f of x is equal to x to the power of 2. Let's use the definition of limit. So again, f of x plus age is equal to x plus age to the power of 2, and so on. We compute this power, we subtract by x to the power of 2, x squared, and we get two terms. Here the x squared simplifies and we get age squared over age, that's one, and then we get 2age divided by age. Here the ages simplify, and again here, so we get the limit with respect to age plus 2x when age approaches 0. But, well, age here is free to approach 0, doesn't matter at all. So could be 0. And then we get that the limit, or better, the derivative of x with respect to x, whatever x is, will be equal to 2x. Now let's look at the geometric interpretation of the derivative. And the derivative of a function is, in one point, is the slope of the tangent line to that point. That's because we can write the y as here is the derivative of x computed in c times x minus c plus f of c. You see that this is the slope and this times this is the intersect here. Disclaimer: not all functions are differentiable in some points. For example, you can recognize the middle one. Of course, we cannot compute the limit here. How can we pretend to compute the derivative onto with respect to a? Here, for example, let's start from the left. If we approach from the left or from the right, we get different results. Here we cannot compute the limit. So differentiable functions are continuous, but not vice versa. These, the left picture and the right picture, are continuous functions. But we've seen that these are not differentiable functions. So differentiable function guarantees us that those functions are also continuous, but not vice versa. In the example with x to the power of 2, we have used to take advantage of the definition of the derivative with using limits to compute a sort of rule, derivation rule. We can do this the same for scalar multiplication, sum, products, quotients, and so on, composition of functions, and so on. And we get some rules. In fact, the great advantage of derivatives is that we can compute them in an algorithmic way, in an algorithmic manner. Thanks to these rules, we have just to apply them. For example, we have that the scalar multiplication rule. We have that if we take the derivative of lambda times the function, then the this results to lambda times the derivative of the function itself. Simple. Again, here we see that the derivative of the sum of two functions is the sum of the derivatives. These are remarkable derivation rules. There are a lot of others that we will not cover right here. Just to another point, the chain rule. The chain rule describes how to compute the derivative of a composition of functions. In fact, here you can see the circle that denotes the composition. So what we are computing here, we are computing the derivative of g of x, f of x. And this is the result, but we will see in more detail in the next slides. But since now we have covered simple functions that map a real number to another real number. Now let's take a look to functions that go from Rn to R, multivariate functions. Here we cannot make use of derivatives, but we have to define partial derivatives with respect to one variable, because here we have n variables, a n-dimensional domain. So to take a small variation, we have to choose the direction of this variation. For example, in here we express the partial derivative. You can see this symbol that describes that we are talking about partial derivative with respect to what direction, the jth. Well, we are just computing the usual formula, but applying the plus age only to the jth dimension. That's it. Very simple. Now we can collect the partial derivatives with respect to all n directions and wrap up each of these terms in a vector. This is the gradient of the function. Can be also written as a derivative here, but we are talking about a multivariate function now. So the gradient of a function is just the concept of the derivative scaled to multivariate function and a little bit complex spaces, real spaces. This symbol is said to be nabla, a geek symbol, and is also written as gradient operator. The gradient operator can be expressed as a row or column vector. It depends. Here I use the notation of row vector, but we will see in a minute that using column vectors could simplify the notation sometimes. In fact, usually in physics we use gradient as a column vector. So we want to measure the instantaneous rate of change of a function with respect to the point x0 and the direction given by a vector v. Now we don't want to compute the measure of instantaneous rate of change, but using a specific direction given by a vector. So what we want to compute here is a directional derivative of the function f with respect to the vector v. How can we do this? Well, we can define the directional derivative in the same way, in a very similar way of the usual derivative, but here the variation using age is computing referring to the direction we want to compute the directional derivative, which is v. So we take a close step with respect to the direction of v. This can be written as the dot product between the gradient and the vector itself, the vector v itself. And this is an example of how we can imagine the directional derivative. We have a function that goes from a 2D plane to a real number. So the function can be drawn in a 3D space. We compute the derivatives with respect to the usual axis, and this leads us to the usual gradient. But now then we have to adjust this gradient with respect to the direction we want to compute the directional derivative. And this sort of adjustment process, remembering what we have seen in course 2, the analytic geometry, can be done using the inner product. So we take the gradient and we do the inner product of the gradient with respect to our direction. Here, for example, we can see the directional derivative with respect to a vector that lies onto the particular plane. Geometric interpretation of a gradient. Well, since the gradient is a vector, we can express that vector using the canonical basis. And it means that we have, for example, the partial derivative with respect to the x-axis times the canonical basis that refers to that x-axis, and so on. Now, these coefficients are the partial derivatives, and every one of the partial derivatives tell us how fast the function is changing with respect to the standard basis. So at a given point, the direction of the steepest ascent is in the same direction of the gradient. Why? Because of the derivative. In a univariate function is the steepest is the slope of the tangent line. Now, scaling this up, considering just one direction here, we can say the same for the partial derivative. Wrapping up together using the canonical basis, we get the direction of a steepest ascent is in the same direction of what? Of a gradient. For example, let's take a look proving this with the concept of directional derivative. And to do so, we get v a unit vector. And we want to find v such that the directional derivative is maximum. The directional derivative can be written with respect to a generical unit vector v is written as the dot product between the gradient and the v itself. But the dot product can be written using the definition of cosine of the angle between the gradient, which is a vector, seen here is a vector, and v itself. So we take the norm of the gradient, the norm of the unit vector, and the cosine of the angle between the two. Note that v is a unit vector, so this is equal to 1. So we want to find v such that this the directional derivative is maximum. What we find here is the norm of the gradient, while it does not depend on v, but the cosine of theta depends implicitly on v, the direction of v. So this argmax will be v, the w, in which w is the vector, such that the cosine of theta is equal to 1, which means that the w and the vector w and the gradient point in the same direction. They are overlapping. So again, we are proved that at a given point, the direction of the steepest ascent that we want to find in v is the same direction as the gradient. Why? Because the cosine between the steepest ascent and the gradient lead us to the cosine of that angle equal to 1. The two are overlapping. The gradient, in this sense, is a vector and can be represented here with its components that are the partial derivatives. Also, for example, in physics, the gradient can be expressed as a vector space, as a vector field. But, for example, here is the projection of the vector field of the gradient with respect to a plane, to the plane. In fact, we can compute the gradient for each point of this function. And we can take, for example, the only two components, not the z component of the and get this representation. What we can do when we are dealing with multivariate function, but with a function that goes from Rn to Rm? Well, the result will be a column vector with m components, f1, fm. But we can do for each of the components the same process to compute the partial derivatives. So here, while the gradient was a vector, here we are getting a matrix, an m times n matrix. In fact, here we say, okay, I have just to apply to express this as partial derivatives with respect to their n directions. But f is a column vector, and so I write it down to get this matrix. In the Jacobian, has a particular geometric interpretations that will be exploited in the next course, talking about probability and change of variables in statistics. Imagine here we have f that goes from Rn to Rn, the same space. So we are doing a change of variables. Then, for example, given these two vectors, we have that the functions give us this deformation. Well, the Jacobian at the points give the best linear approximation of the distorted parallelogram near that point, and the Jacobian determinant give us the ratio of the area of the approximating parallelogram to that of the original square. So how the volume changes, which is the determinant in some sort. No? Now I want to take a deeper look to the chain rule, because it's very important. The chain rule is very important. It's a very important tool in machine learning. And to do this, I will refer to the example taken from Mathematics for Machine Learning, but by these three authors. So let's consider a function, age, and age is a composition of two functions, f and g. That's why we are using the chain rule. We are referring to a composition of two functions. So g from a real number gives to us a vector of two components. Then f takes these two components, these vectors of two components, and return to us a real vector, a real number. F is expressed as the exponential, and g instead is expressed as t cosine t, t sine t. In fact, g takes, for example, as argument t and returns to us a 2D vector. F takes a vector, in fact we have a bolded x, and computes this sort of exponential. So we want to compute now the gradient of age with respect to t. Remember that age is the composition of f composed g, g composed f. So here we have to apply the chain rule. So this is equal to the partial derivative with f with respect to x, and x is its argument here, but x here is expressed as a function, is the result of the application of a function g with respect to t. So we have to compute how x changes with respect to t with this red partial derivative. This partial derivative is actually a gradient. Moving a little bit further, we have just to compute the how f varies with respect to x1, with respect to x2, and then we have to take the first component of x, which is x1, this one, t cos t, how varies with respect to t, and this is the derivative. We will not care about the result. It's just to prove you how to compute the chain rule. But now let's look at the chain rule in a more abstract way. taking the gradient of a vector with respect to a matrices. Here we have a function that goes from Rn to Rm and can be written as the multiplication between a matrix and the vector, the input vector. So we are expressing f as a multiplication between the transformation matrix and the input vector. So f could be a linear mapping. And we want to compute the gradient with respect to what? To A. Well, the gradient here has 3 dimensions. Is three-dimensional gradient, so we do not refer as a tensor, not as a vector, but as or a matrix, but as a most generic tensor. Let's do it one step to another. We start by expressing f with its m components. Okay. Next, our goal is to compute one of these components in a more generic way. So we have this sort of partial derivative of fi of x with respect to the matrix A. So we are getting that this is still a tensor, but has 1 times m times n dimensions. This can be seen flattening, so giving up this dimension as an m times n dimension. So this expression can be decomposed in a matrix in which this matrix A is seen by its components ay1, a1n, am1, amm, and so on. Now we want to compute the result of all of these elements, all of these partial derivatives, that these are actually a number now, because this is a scalar and this is a scalar. F of I is expressed as the multiplication between the ith row of the matrix I and the vector x. And then we have the this should be with this in mind, we have to compute the partial derivative. But remember that the derivative is a linear application. In fact, there's the sum rule, differentiation rule, that says that the differentiation of a sum is the sum of the differentiation. Now we have the sum of the differentiation, but we can see more, because x here, since we are computing the derivative with respect to aiq, means that xj here is a scalar. So you remembering the scalar differentiation rule, the scalar term goes out of the derivative. Now we have the derivative of one element with respect to another, the sum. But this derivative will be equal to 1 only if j will be equal to q. So we are taking the derivative of one element with respect to itself. Otherwise, if J is different from Q, then these two will be uncorrelated. So here we have that this derivative is equal to xq if E equals P. E equals P. That goes here. Otherwise, it's 0. So what we are getting here is that a matrix that has only one non-zero row. And these, what are the xq's. xq's here is the column. So x1, xn. This matrix can be written as a stacking of row vectors. Now we go back, and with this in mind, we can say that, okay, this is almost equal, since this is a tensor, but is 1 times m times n. That is similar to this expression. And then we want to go back to find this greater expression. When we apply the chain rule in this sort of way? Well, we can apply the chain rule in this way in neural networks, a particular algorithm that can be represented in this way, in one of its simplest form. And let's take a look to this hidden layer, it's called. In this one, for example, we have 3 inputs, 4 hidden layers, and 2 outputs. One of these nodes of the hidden layer means that this node is receiving 3 inputs and it's mapping out 2 outputs. It's a function then. In fact, this function can be written as: I take the inputs, the 3D inputs, I apply some sort of weights, I multiply the weights to the input, the red input, I apply then to this result an activation function, and then I get back this age of x that with all of the other nodes, so I have 4 of this age of x, will be computed together in the output nodes. But what is the gradient of age of x of one of the hidden nodes with respect to the weights? Well, we have to take care of the activation function, remembering the chain rule, and then we have that what is inside, we have to perform the partial derivative of what is inside here, we usually expressed as S of x, and this matrix, the weight matrix. This is a simple computation, especially for the usage of simple activation functions. And then we have these partial derivatives that we have already computed in the slides, in the previous slides. So we have defined limits. We have understood how we can take advantage of limits and compute changes and rate of change using differentiation, derivative, gradients, JACOBIAN matrices, and the directional derivatives, and so on. Now, in the next section, we will see how personal computers are able to use the differentiation rules to compute derivatives.